What really exists at the farthest reaches of our solar system? For years, we believed we had a solid understanding of our cosmic neighborhood's basic structure. But recent discoveries are now upending those assumptions, leaving experts both amazed and puzzled. What surprising insights have scientists uncovered from the data sent back by the two Voyager probes? And why are we now forced to rethink our fundamental view of the solar system? Today, we'll take you on a journey through space, time, and groundbreaking research that could completely transform how we see the universe. Make sure to watch until the very end to get all the details behind this fascinating revelation. Our solar system isn't simply drifting aimlessly through space. Instead, it's wrapped inside a vast bubble of particles emitted by our powerful central star, known as the heliosphere. These particles stream outward in every direction, mostly as solar wind, forming an invisible shield that envelopes us. This natural cocoon protects us from the constant barrage of radiation and particles coming from interstellar space. The heliosphere stretches out to roughly twice the distance of Pluto's orbit, ending at the heliopause, the outermost boundary of our solar system's protective shield. This boundary marks where the influence of the sun, our source of heat and life, fades away. But this region is far from simple. It's a complex zone where solar wind plasma meets the sparse gases of interstellar space. Here, particles collide, magnetic fields interact, and electric currents and shock waves form. The result is a cosmic dance that scientists have yet to fully understand. For a long time, this region existed only in theory because we lacked the technology to explore it directly and gather detailed data. Thankfully, that changed several years ago thanks to the two aging spacecraft Voyager 1 and Voyager 2, launched on August 20 and September 5, 1977, respectively. The ancient Voyager probes are now nearly 25 and 21 billion kilometers away from the Sun, respectively. No other human-made object has ever traveled so far into space, which is even more remarkable considering that Voyager 1 and 2 were never intended to achieve such milestones. Their original mission was simply to explore the outer planets of our solar system, which were largely unknown at the time. But there's more to the story. The twin probes were initially expected to operate for only about 5 years. Yet, they far surpassed those expectations and eventually ventured into regions previously unexplored by any spacecraft. Despite being launched in an era when computers occupied entire rooms, Voyager 1 and 2 made history by entering interstellar space in 2012 and 2018, respectively, an achievement no other spacecraft has matched. What they encountered beyond our solar system was as surprising as it was fascinating. Instead of a sharp boundary, both probes detected intricate magnetic field patterns, flowing streams of plasma, and even a continuous hum generated by interstellar plasma oscillations. The exact source of this hum remains a mystery, but it clearly reveals that the edge of our solar system isn't a lifeless void. Instead, it's a dynamic frontier where cosmic forces collide, matter interacts, and new structures emerge. Considering the vast distance and age of the Voyager probes, it's truly astonishing that NASA can still communicate with Voyager 1 and 2. Specifically, NASA relies on the Deep Space Network, a worldwide system of massive antennas designed to detect extremely faint signals even weaker than the light from a flashlight shining on the Moon. Because of the immense distance, it now takes about 22.5 hours for a message sent from Earth to reach Voyager 1, and the same amount of time for the probe's reply to return. Once the signal arrives back on Earth, it is decoded into data and analyzed by scientists. Despite facing significant technical challenges over the years, often causing considerable stress for NASA's experts, the Voyager probes continue to deliver invaluable and unique insights from the fascinating realm of interstellar space. In fact, some of the data they send back could completely reshape our understanding of the structure of our own solar system. Mysterious structures lie at the outer edge of our solar system. There's no doubt that the data from the Voyager probes is a scientific treasure trove. However, these probes can only reveal conditions at their specific locations. As mentioned earlier, the heliosphere is an enormous structure. But how can we create a complete picture of such a vast region when it has only been directly explored at 2 points? One approach researchers use to map the heliosphere, including the heliopause, on a broader scale is by detecting emissions of high-energy neutral atoms, ENAs. These ENAs form through interactions between the solar wind and the interstellar medium. Still, much of this transition zone remains hidden. That's why it was such a breakthrough when a team led by Eric Zernstein from Princeton University managed to uncover new details about this mysterious area just a few years ago. This discovery was made by examining a months-long rise in the dynamic pressure of the solar wind recorded in 2014. After this increase, NASA's Interstellar Boundary Explorer, IBEX, satellite detected a striking brightening of high-energy neutral atoms. This revealed movements in the heliopause and notable asymmetries in the heliosphere's structure that challenge our previous models. Zernstein explains, in early 2017, we observed a brightening of high-energy neutral atom emissions in the IBEX data coming from a small region about 20 degrees below the heliosphere's nose. Initially, this brightening appeared at the highest ENA energies, but over time, the emission area expanded and became visible at lower ENA energies as well. We understood that this was a reaction to a significant change in solar wind pressure, which plays a crucial role in ENA emissions at the heliosphere's boundaries. The fact that the brightening spread unevenly across the sky ultimately led experts to pursue further investigations. A closer examination of the IBEX data revealed that the heliosphere's surface is warped by massive waves appearing at surprisingly tilted or oblique angles. These waves can vary by as much as 10 astronomical units. That's 10 times the distance between the Earth and the Sun. This means the heliopause isn't smooth or uniform as once thought. Instead, it's threaded with wavy regions that differ in density and temperature. This unexpected complexity in its structure caught scientists off guard. But what causes this rippled appearance of the heliopause? Researchers suggest it results from reflected waves of energized particles bouncing back and colliding with the charged solar plasma. This interaction unleashes a storm of high-energy neutral atoms, which in turn push against the heliopause, creating tunnels through interstellar space. While the heliopause marks the known boundary of the heliosphere, recent observations indicate far more intricate structures exist beyond it. One intriguing theory, supported by data from the Erosa X-ray telescope, proposes that our solar system might actually be linked to a much larger cosmic structure. This describes what's known as the local bubble, a region in our interstellar environment that's mostly free of dust, composed mainly of neutral hydrogen and a very thin, hot plasma. Scientists believe it was formed by multiple supernova explosions. What's fascinating is the idea that these interstellar tunnels serve as connecting pathways between several such bubbles scattered throughout the interstellar medium. Together, they form an enormous network of cavities spanning countless light-years, created by the explosive deaths of massive stars. But this network isn't just important for shaping the dynamics of interstellar space. It might also explain the unusual behavior of magnetic fields and particle flows observed in certain areas. Supporting this theory, data from the Voyager probes reveal noticeable bends and shifts in the interstellar magnetic field, suggesting that our solar system could be located at the entrance to one of these tunnels, or may have already passed through it. All of this indicates that interstellar space is far from being a uniform, empty void. Instead, it is a complex and dynamic environment that plays a crucial role in shaping our home system. If the tunnel theory is confirmed, it would profoundly change how we understand our cosmic surroundings. This would imply that our galactic neighborhood is composed of distinct zones, transitional regions, boundaries, and potentially even unknown physical phenomena. Data from the Voyager probes serve as an essential foundation for future exploration and interpretation of interstellar space, such as NASA's upcoming Interstellar Probe mission. These insights assist in planning trajectories, calibrating instruments, and identifying key target areas.